All right, we're going to do a couple of quick problems from the review, the Mod 3 review that a student has asked about. They asked about 5 questions. The first one, though, was about number 12 on the Mod 3 review. This is actually from the 5.2 homework, and there is a video that goes over this very same problem that I posted in the announcement. So if you're wondering about number 12 on the review, go back and refer to the video I have posted in the announcements. It says something about graphing exponentials and logarithms in MyMathLab, and it will go over that very same problem. But let's look at number 17 from the review. So let me get that up on the screen.
It's not on there, so you'll have to just click on that and then open it up.
I don't know that it will show that. I think I have to go here first. Oh, it was that thing. I didn't do that. Where did that go? All right, sorry. Hang on a second. Let me find the review again. Because I think if you don't have it already open, it won't.
Yeah, you'll have to then go back and share that particular problem.
All right, so there's the problem.
Okay, so now you just have to go find it.
Now I have to share. Try it again. Let's share problem. Right there.
Yeah.
Okay. Here we go. So number 17 is asking us to solve a logarithmic equation, and it says use an exact answer and using E as needed. So this means we're not going to be doing estimates on our calculators when we get to the logarithm step. So I'm going to write this on my paper, and then we are going to switch over and work this on our paper together. 9 times natural log of x equals 39. All right, so let me switch back to, I thought the default camera was supposed to be in my notebook, but okay. All right, so this is number 17, and it says it wants us to solve for the x. So here we go. You have to be careful. Don't forget with logarithms, you always want to keep in the back of your mind that they have a restricted domain. So even once we finish solving, you want to make sure that your answer, if you plugged it in for x, the value inside the logarithm would be a positive number. So I'm just going to say that up front just in case something weird happens at the end. But all right, first of all, much like when you're solving for exponentials, when the variable is inside a logarithm somewhere, you want to move things around the equation so that you have isolated just that little piece that's the logarithm. So if you have 2 separate terms, you're going to add or subtract your term that's not part of the logarithm term to get rid of that number. That'll be 9 times natural log of x. 39 minus 3 is 36. Okay, next thing we're trying to do, we're still trying to get the x by itself. It's part of the logarithm. We still have something outside that logarithm, which is to times 9. So to eliminate multiplying by 9, we're going to divide that 9 on both sides, and that will give us natural log x on the left. 36 divided by 9 is 4 on the right. Okay, when you get to the point here where you have your logarithm isolated, then you can, there's several ways to explain it. I'm just going to use the idea of inverse functions. So the inverse function to taking a logarithm on x is to raise this whole thing to an exponential function where the base of the exponent matches the base of the logarithm. Remember, all logarithms have bases. So ln of x really is one of our understood bases of e. So ln means natural log, which means the base of e. So this is the base we're working in. So there is a basic rule with logarithms that says if you have some sort of base logarithm, I'm just going to do this as an example before we go back to this. All right. If you take that and you take a base b logarithm and you use it as an exponent on that same base, so b to the log base b cancels each other out the same way. And that's what we do to get rid of a logarithm, is we use this expression as an exponent on a base, and the base has to match the base that we're dealing with. So natural log and e are inverse are associated together because they have the same base. So what I'm going to do is I'm going to use both sides of these. They're going to become an exponent on e. So it's kind of like just writing an e underneath both sides here like this. So I'm basically taking these and using them as exponents on e. If these two things are equal, if I raise e to the same number, that should still be equal. So whenever you want to get rid of a logarithm, figure out what base you're working in, and then just use that base under both sides of your equation, and both sides of the equation will turn into exponents. But this is why you do this, because a logarithm and a matching base cancel each other out, whichever way they're used, and that just gets us the x value. So x is just going to be e to the fourth. There wasn't any other number with the x inside the logarithm, so when we're finished with getting x by itself, this is done. I did say make sure before you put this in your final answer that e to the fourth, whatever x is equal to, if you plug it back in for the x in the original equation, you do end up taking the logarithm of a positive number. So this is just plain old x. So if x is e to the fourth, e is a positive number, you raise it to the fourth power, that's a positive number. It's definitely going to work. But like if this said x like minus a million, you could put the e to the fourth in there and you could take that, which is something less than a million, subtract a million and get a negative number in here, which means it wouldn't work. But e to the fourth is fine. All right, maybe too much talking. So that's what we're going to put into the problem. We do not want to get out our calculators and estimate what e to the fourth is approximately. It says use exact answers, use e if we have an exponential thing. So that is our exact solution. So when you're solving exponential problems where the x is inside the logarithm, you're going to get, when you're solving logarithm equations where the x is inside the logarithm, your exact answer usually involves the matching base of a certain power and perhaps something else in there. All right, so that is your exact solution of number 17. I'm not going to go back and put it in there. I'm going to go ahead and skip to the next problem now. So let's go and see what our next problem is. It would be, let's go back to here, number 17. Let's look. The next one in our list is the very next one, number 18. And it's a similar type of thing. We're going to have to solve for the x, and the x is in a logarithm, but this time we're working in base 6, and we have a couple of logarithm terms on the same side of the equation. So that means we have an expression with more than one logarithm. Okay, I've written that down. So let me go over to my notebook again. Okay, this is number 18. We're trying to solve for this x, and there's some mystery number that if you evaluate it with log 6 and then you evaluate this log 6, they add up together to make 1. So we're trying to figure out what number goes here so that all this adds up to 1. Okay, so when you're solving for a logarithmic equation and you have logarithms in multiple terms like this, added or subtracted, what you want to first do is combine your two logarithm terms together. Now that's assuming that we have a 1 here, that we don't have some other number in front of it to have to deal with. That's a whole other operation where we would move that number. But if we just have two logarithms with the matching base like this, there is one of our logarithmic properties, this was from section 5.2 as well, that says if you want to combine both logarithms into a single logarithm, you can do that as long as, this is kind of counterintuitive, you multiply the two inputs together. So you can combine these two basics. If it says plus, you're just going to multiply x times 9. I'm going to write it as 9x. So that's a key step right there. If you don't know how to do that, that's one of the things that we're trying to teach you in this chapter is if we are dealing with something with logarithms and you have multiple terms with the same logarithm, let's first combine them into a single logarithm. That'll make it simpler, like the one we just did. But you have to multiply the two inputs together, 9 times x. Okay, now from here, we're back to what we were doing here where we have to apply a base basically on both sides, a base that matches the logarithm we're working at. So we're working in base 6. So we're basically going to use these expressions on both sides of the equation as exponents on 6. And it's getting to be feeding time for the dogs, and so you're going to hear a dog whining around my feet here. You'll just have to be patient. Okay, so if we want to get rid of a base 6 logarithm, raise it to the power on a 6 base, and they cancel out. That leaves us with something that's very easy to solve for. It just says 9 times x equals, go ahead and work that out. This one's easy because it's 6 to the first, and then divide both sides by 9. So it'll be 6 over 9, which is a little more simply written as 2/3. Make sure that if I plug 2/3 in for x, which is right there, and work out everything between the parentheses, it gives me a positive number, which it does. So it is the solution. So again, there is our exact solution. It's going to be 2/3. All right. Let's look at the next problem. We have 21 and 25. So number 21, I think we're getting into solving some equations here. So let's look at number 21. Okay, so this one is kind of a interest rate kind of problem. We have some exponential growth here. So it says the future value of investment of $50,000 at 7% compounded annually. So that means one time a year. And then they give us the actual function already written out. We don't have to put it together. And how many years will the investment grow to? And it gives us some future amount. Okay, so when we're looking at this function right here, the t is how many years, the 50,000 is how we're starting, the starting amount, it says $50,000, and then what it's calculating is what this s represents is the future value after t years. So in this case, it's asking us to solve for the t because it says in how many years, and they give us that future investment. So we're going to take and set up an equation where we use this $120,000 number across the equal sign. We're going to set the function equal to that value. So that's what I'm getting ready to write down on my paper, and then we will switch over one more time here. So 120,492, that seems very specific. So I'm betting maybe we could also just scroll through our table if we wanted to do it a different way. 50,000, 1 plus 0.07 to the t. That's the other dog that's getting hungry. Okay, so let me go to my notebook here. All right, so we set the output that they gave us equal here, and we're going to solve this using the algebra because that's what we're trying to show you, but we can also do it with graphing at another time. But for right now, we're trying to solve for t. It's in the exponent. It's an exponential equation. So that means there's a base associated with it. So we need to get rid of anything that is not part of the base of the exponent. So we're going to divide that 50,000 since it's 50,000 multiplied in there. Oh my goodness. Yeah. Okay, now I'm going to go ahead and add the 1.07, the 1 and the 0.07 together. So that's the right-hand side looks a little easier, and then I'm going to have to actually get the calculator out. 120,492.25. We're going to divide it by 50,000. And that gives us 2 point. Now I should just probably leave it as a fraction, but this does actually divide out into a certain number of places. If it went all the way across the page, that means it doesn't really reduce, but this does reduce when you're dividing by anything with a 5. So I'm going to go ahead and use all of the numbers that it gave me. If you're going to ever calculate something in the middle of a problem, make sure you use all the digits. So what we have now is we have an exponential statement over here where we have the base and the exponent isolated. Okay. All right, and then over here on the other side is the combination of those two numbers. So we're going to get rid of the base so that we can get the t by itself. So we're going to take a logarithm with the same base as what we're trying to get rid of on both sides. Now, if you look at this, if you look this up online or in the view an example back in the homework, they may show you a different way to do it where they take a natural logarithm every time and then they use a power rule and all that. Just as easy or just as valid of a way, but I'm going to do this with the fastest way, which is the inverse operation of a base of 1.07 is a log with the same base, 1.07. So what I'm going to do is apply a matching base logarithm to that expression right there. And those will cancel. But if I want to do this, I have to go over here and do the same thing. So I'm going to apply a log with a base of 1.07 to that whole number. These will cancel. And that's done. And this is the exact value of the answer, 1.07, 2.409,845. And then I need to, if it says to round, let me see if it says to round to the nearest whatever. It says, do not round until the final answer and then round to the nearest whole number. Okay, so that's what I'm going to do. I will just do this here rather than try to switch over another screen. So when you do a logarithm with a different kind of base, that is located in the math menu. So if you go to the math menu and you go way, way down there, or sometimes it's faster to just scroll up. But if you go, I'm trying to find a way to make sure you can see everything here. Look for something that says log base, because that's what you're trying to do. There it is. So log base means it's going to give a space to put that log base in there. So see there, it has a field. My log base that I'm working in is 1.07. And then the number that I'm actually taking the log of is this number that's right above here, 2.409845. And then I don't need that. But what I do need to do is, okay, so there it is. That is exact. If I want to know to the nearest whole number, the whole year, oh, it turned out to be exactly 13. That was easy. All right, so this turns out to be 13. So that means in 13 years that $50,000 will have grown to that oddly specific value. It's specific because someone worked backwards from a whole number answer, obviously. But anyway, that also means other ways we could have done that, since it's so strange. We could have put the function into our calculator. Here, let me switch one more time over to the graphing calculator. It'd be easier for you to see if I just put a calculator on the screen. So I did it algebraically. Sharing is paused until you return to the shared window. What does that mean? Let me try that again. Okay, I think that looks fine. All right, so we're going to, do I have two of these open? Okay, so 50,000 and then 1.07 to the power of E. I'm sorry, to the power of T, which is really X when you do something like this. This is the original problem. It said, when is X going to produce an outcome of 120,402.90 cents? So I'm just going to go to my table and see if it's in there, because it sounds to me that's such a specific number that I bet they got it off of here. So look right here at 13. So these are the answers that you get when you change the X values by a whole number. So the advantage to this is, because we know it already, because we did it the other way, that the X value we're looking for is a whole number, we should see the exact value they asked us for over here. The disadvantage of looking up your answers with a table is, what if the answer that you're looking at is somewhere between the 9th and the 10th year, and so the output they gave you was somewhere between this 91,000 and 98,000. If they said, when's it going to be 95,000? Well, we don't have 95,000 in the list, so we would have to find the answer some other way. But in this case, since the answer was so oddly specific, and if you look down here, you can even see it expands to there's our and the 25 cents. So you could also just try this, put the function into your calculator, go to your table, look and see if any of the numbers in the Y column, the output column, match the number they're asking you about, which is right there. And then look over here, and the X value is 13. So